It is my real pleasure to introduce Elliott Shue, who will be the speaker today. Elliott has a first-class pedigree. He comes from Stanford, Cornell, and Chicago. He came here when the University of Arizona was sort of leading a charge to try to create, be part of a collider that was going to take over an enormous area in Texas. It was killed by the government because it was too expensive. And from there, somehow or another, we ended up with a Large Hadron Collider, which is in Switzerland, which is what we're going to be talking about today. Elliott is part of the group at the University of Arizona that has been part of one of the detectors that famously measured the Higgs boson. Again, one of these incredible things that's been happening lately in physics. That was a few years back. Elliott bet on the wrong horse at that point. He was betting on a thing called supersymmetry. So then he decided to quit that. I'm just kidding. So Elliott has gone from his interest in supersymmetry to dark matter, and I think everybody here has already heard it one way or another that the universe is composed mostly of dark matter and dark energy. We don't really know what any of these things are about. And Elliott has been working hard at trying to figure out what dark matter is all about. But Elliott is one of these sort of multiple threat kind of guys. Elliott was my associate dean in the College of Science. So if you ever go to the Tucson Book Festival and you talk about the Science City, it was Elliott that got all that stuff going. When you talk about science cafes, Elliott's fingerprints are all over that. When you talk about many of our undergraduate students in the College of Science, about 70% of them being involved in undergraduate research education. In other words, they're stuck in a lab somewhere doing some fantastic research. Elliott's fingerprints are all over that. Elliott just took over being the interim dean of the college, of the Honors College, which will benefit us greatly, and of course, many of our students. And last year, he was also honored by the university by being a distinguished professor, which is one of the highest honors that the university can bestow on its faculty. So it's my great pleasure to introduce to you Elliott Shue.
Thank you very much. Thanks a lot. Thank you, everybody. I guess one of the problems with working with the dean, it's not really a problem, is that sometimes you tell him things and they become his first joke. So I did work on supersymmetry. We're now turning our attention to dark matter, and I'm hopefully to tell you about earlier. Also, it's a real challenge to come after a 15-year-old prodigy. And I don't know what I have nothing left to say. So hopefully you'll hear something. But actually, the other thing is, being the interim dean of the Honors College, at least until they kick me out, is that we can probably offer him a place, and he would be a perfect example of somebody who would make a great fit at the Honors College. So as you've seen, we have a flock of physicists. That wasn't my term, but we have a flock of physicists up here who have told you about things like what physicists do to black holes, to gravitational waves, and today I'll talk to you about particle physics. And if you look at these pictures, and then the last one you'll hear next week is Pierre Meister, who's somewhere in the audience here, who will talk about quantum physics. You'll notice something very striking about all these faces that you see here. And yes, you're correct that 4 of these people are theorists, and I'm the lone experimentalist. So today's talk will be about how to look at what we do from an experimental point of view. And really the idea is that that while we have this kind of ongoing, I would say, rivalry between the theorists and the physicists and the experimentalists, sorry, that was a slip of the tongue, between the theorists and the experimentalists, we actually work hand in hand, and I'll try to show some of that. But sometimes, the theory is going to precede what theorists will come up with a theory, and that will actually drive what the experimentalists will do. Sometimes the experiments will find something that the theorists had no idea even existed. But what's most interesting, at least from my point of view, is that when the theory and the experiment come into conflict, when there's a tension, where there's an experiment that sees something that the theory doesn't expect, or the theory expects something that the experiments don't see, that actually leads to some of these big revolutionary things that happen. And so I hope to kind of bring that out today. But in particular, what I'm going to talk about, oops, that went sorry. That is right. What I'm going to talk about today is basically what are we made of, what holds these things together, and then kind of the big question, what's missing? And I'll hope to give you an example of that when we talk about dark energy. But let me walk back a little bit and talk about this thing called the Standard Model. And Dr. Dinas did a really good job of explaining what all these dots mean. Basically, the way I think about it is that everything on the left-hand side, those 12 particles, are what everything that we know of is made of. It's the matter. And Dr. Dinas said that, well, these are the, if we were to kind of break this down to grammar, those would be the nouns. The things on the right are the forces. Those are the things that actually hold everything together. So for instance, the photon is the carrier of the electromagnetic force. That's actually the thing that holds everything that we're looking. The stage I'm standing on is solid because of that electromagnetic force. And then we come to the Higgs. Oh, and by the way, the forces are kind of like the verbs. Remember he said that we have nouns, we have verbs. Well, the Higgs does two things, actually. Dr. Dinas said that it's the adverb. It modifies these forces. But actually, it also does something else. The Higgs, in addition to modifying the four forces that you see on the right, or giving rise to the four forces that we see, also gives mass to the particles that have the matter particles. So in fact, the Higgs in some ways can be thought of as an adjective or an adverb. This morning I tried to Google a word that meant what's an adverb and an adjective. Couldn't find anything, so at the breakfast table I asked my daughter, she's going to be embarrassed, but I asked her, so what is a word that means both an adjective, that a word can be both an adjective and an adverb? And she said, why do you want to know? And I said, well, I'm giving a lecture tonight and I thought I'd use that in my lecture. And she says, well, then you should have figured that out a week ago. So anyway, there we go. So this model that we have describes everything that we know about matter. That's what matter is all. This is what we know about matter. And it actually is interesting because if you look at, Nobel Prizes were given out first in 1901. And in the years since 1901, up to very recently, this is a number of Nobel Prizes that actually were awarded for the discovery of that model that I just showed you. So about 40 Nobel Prizes were actually devoted to discovering this. And that actually kind of demonstrates to you the significance of this enterprise that we were launched upon. But what I want to talk about is, in particular, the one about the Higgs mechanism, because that's the one that's been most recent, that's one that you've heard about in recent times. And the Higgs mechanism started with these three men. Actually, the unfortunate thing is everybody knows as the Higgs mechanism, it's actually to physicists called the Bru-Englert Higgs mechanism, the BEH mechanism. Unfortunately, all of you know it just as the Higgs mechanism. And what they had done was that they had figured out a way to actually talk about both the electromagnetic force and the weak force in a consistent way. And that way has now become called the Higgs mechanism. Interestingly, Victor Weisskopf said particle physicists are so desperate these days that they have to borrow from the new things coming up in many-body physics like BCS, which is the theory of superconductivity. And perhaps something will come of it, said Victor Weisskopf in 1960. Well, what came of it was the Higgs mechanism. So they actually were looking at other theories. The first paper that Peter Higgs actually wrote was sent to the top journal in Europe called Physics Letters, and that journal rejected it. So he turned around, rewrote it, and they actually predicted something called the Higgs particle, resubmitted it to a journal called Physics Review Letters. And Pierre Meister, who's going to talk next week, is the editor of that journal. And that's the most prestigious journal, by the way, in physics in the US. Actually, I would almost say in the world, but that's just me. It was accepted, and at the same time, the paper by Robert Bru and Francois Englert also was submitted just about a couple weeks ahead of time. They were published together, and what were they looking for? Well, prior to recently, what they were looking for, what their theory said was that we should find a particle called the Higgs particle. And up until until recently, but the time that we started really getting, I started getting particularly involved in the LHC, nobody had found the Higgs. It's actually interesting, I was listening to a lecture by Brian Greene, and he said that when he went to graduate school in the 80s, it was so thought that this Higgs mechanism must be the theory of the Standard Model that he didn't realize that nobody actually found the Higgs particle when he was a graduate student for many, many months, until after he had been there, somebody said, oh, by the way, that thing hasn't been found yet. And he then realized that it was an ongoing experiment. So what I want to do now is talk about how do we get there. So in my world, you have to do an experiment, and you have to do two things. The first thing is you have to find a source of particles. You have to be able to create this Higgs particle. And we do that by accelerating particles. And the next part of it is that you have to then be able to detect those particles, find out what you actually found. And I'm going to kind of walk you through a little bit about the history of how we went about doing that. The very first particles that we found, so as I talk about these accelerating particles, are particles, what we actually have to do, though, is we have to produce a particle like the Higgs. And in order to do that, you can't just create a Higgs. You have to provide a mechanism to do that. So what we do is we take particle A and particle B, and we collide them together. And if you provide those two particles, A and B, with enough energy, what they will do is sometimes they'll produce a particle C. And that particle C, so this equation that you see on the right left-hand side, E equals mc squared, is that famous Einstein equation. And what it really says is that energy and mass are equivalent. They're the same thing. So if you want to produce a particle of a particular mass, if you provide enough energy, that particle will mysteriously just pop out of air. And so the interesting thing is that in order to do that, to produce a particle with a given mass, you have to provide enough energy. But the mass of the particle that you can produce, the energy is divided by that c squared. So c is the speed of light. Remember last week or 2 weeks ago when Sam Gralla talked about the speed of light? It's a big number. So if you square it, it's an even bigger number. I don't know what it is, but it's a really big number. So in order to get a mass to produce a particle, you have to provide enough energy in the two particles A and B to produce that particle C. So how do we do that? Well, the earliest experiments were done by using cosmic rays. What you see here is a picture of the aurora borealis, which is the result of the solar wind and then other cosmic particles being funneled by the Earth's magnetic field to the North and South Pole. And when those particles hit the atmosphere, they produce other particles, and some of those particles are light, and that's why you get these pretty colors. But in doing that, you can actually have a very high energy particle hitting the atmosphere and producing another particle. The problem with using the cosmic ray, the flux of particles that are hitting the Earth's atmosphere, is that you don't know where they're going to be, and it turns out it doesn't happen that frequently. It's about on the order of like 1 per second or something like that. So while it happens, if you want to accumulate 1 billion of these things, you're going to wait a very long time. So the next mechanism was to actually build something that actually produces a set of energetic particles, and Lawrence here was one of the first inventors to actually produce something called a cyclotron. The way the cyclotron works is that you inject in the very center here a particle which doesn't have very much energy. And when a particle moves in a magnetic field, it goes in a circular direction. It moves in a circular path. So as the particle gets ejected from the center, there's a high voltage supply which accelerates that particle just a little bit. And so as the particle goes across this gap, each side is called a D, as it crosses that gap, the particle gains a little bit of energy. As it gains energy, its momentum increases, and when that momentum increases, its curvature, the path it's tracing, gets a little bit less. So instead of being a small circle, it gets a bigger circle. So what happens is that the particles start at that position A and wind their way outward, and each time they cross that gap, they get a little bit more energy, until at the very end, they exit the apparatus with a very high energy. And so that's a very neat apparatus. The only problem with an apparatus like this is it requires a magnet at the top and the bottom. So if you want to make a bigger apparatus, in other words, one that can have more and more accelerations, you have to have a bigger and bigger magnet. And at some point, you just can't make a magnet that big. His very first apparatus was limited by the size, and it could produce a particle that was going that had an energy of 5 million electron volts. 5 million sounds like a big number. The number we're going to be talking about is hundreds of billions of electron volts. So we're talking about sizes that are not reachable with this technology. So the next technology, so then there's one problem that you have to get high energies. The other thing you have to do is get high rates. In the 1950s, Frederick Rines and Clyde Cohen wanted to try to look for this elusive particle called the neutrino, which had been postulated by Wolfgang Pauli in the 1930s, when he noticed that there was this weird structure in something called the beta decays. And what it caused him to do was postulate a particle that didn't exist and nobody had ever seen. And not only was it not seen, but it would be almost impossible to measure, because a single neutrino, if it went through a certain amount of lead would have to go through a light year worth of lead before it would interact with that lead. Okay, that kind of sounds impossible, right? We can't even make things that are longer than a mile. So a light year is that's a long distance. The astronomers can tell you what that is, but I know it's a long distance. So instead of having a light year worth of lead, the other thing you could do is have lots and lots of neutrinos, because eventually if you get tons of them, not tons, but you get lots of neutrinos, some of them will interact in your detector, and that's what he decided to do. So he decided, well, if I want to get a lot of neutrinos, what am I going to do? And his answer was to find an atomic bomb. So you might say, well, that's not a good reason, but it turns out in the 50s, of course, people were exploding bombs all over the place, and that was his source. He actually wrote a proposal where he said, I'd like to use an atomic bomb to search for neutrinos. Well, it actually was accepted. But he then realized, after a few more calculations, that there's a better way to do that, and he went to a nuclear reactor. This is Savannah River reactor, where he could sit outside the reactor and look for a source of neutrinos. If you turn off the reactor, the source should go away, and eventually he actually discovered the neutrino. And when he did, he sent a telegram to Wolfgang Pauli, now this is 20-some-odd years later, saying we found the neutrino, and in fact, it does take a light year of lead to have one interact. The only problem with a reactor is that the particles that are produced from it go off in all directions. So you'd like to have something that has both high rate, high energy, and that comes to the next progression, which is called a synchrotron. And this is the design for things that we now use pretty much all over the world. This is the design of current-day accelerators. The big point of this is that rather than having a big magnet sitting in the center, you can actually locate those magnets around the ring, because they only have to direct the particle's path where the particles are. You don't have to create a magnetic field in the center, because nothing's there. So what the idea was that if you can put the magnets around the ring, you can actually make a ring as big as you want. And that's what's actually happened. So in the 1970s, a ring was built at the SLAC Accelerating Center, which is outside of Stanford. I actually got to work there. I was very privileged. And that ring had a circumference of 250 meters. That's pretty large. This machine, as well as one at Brookhaven National Lab, was the one that actually discovered the existence of the charm quark. What you'll notice is that the mass of that charm quark is about 1 billion electron volts. So in order to get energies that you can produce particles of very high masses, you have to get to a bigger machine. The next machine is called CESAR, and that was located at Cornell University. Actually, this is kind of it seems like it's a triptych of my school years, but that wasn't the point. The point was that this is the next probably big synchrotron that was built. It has a circumference of almost a kilometer, and you can see that the particle that was studying, the bottom quark, had an energy of 4 billion electron volts. And finally, we come to the Tevatron. Now, this one has a circumference of 6 kilometers, almost 7 kilometers. And this is where the top quark was discovered. Now, notice the difference between the energies. In the bottom quark, the energy is 4 billion electron volts. The energy, or the mass of the top quark, is 170 billion electron volts. And that's why you need such a big machine. Okay, so now I'm going to talk about the detectors. So we've talked about how you get from a very small device, where actually just the cosmic ray background, to what we are now doing, which is to looking at how do we figure out what those particles are. So the story starts with a very simple device. In the top right, you see a device called an electroscope. Electroscope is actually, you see them in physics labs. If you ever take a course from me where we do electricity and magnetism, they don't work very well with me, but you take a detector and it just has 2 gold leaves in the middle. And if you put a charge on the electrode at the top, that charge is distributed on both gold leaves and they separate. And so you know that there's some charge there. Well, people, when they first made these things, soon figured out that if a ionizing particle goes through that, you actually create free electrons that can move around inside the electroscope, and those can hit the gold foil and cause the charge to dissipate away. And so it provides a pathway. So what you can do with such a thing as an electroscope is you can actually take it to various places and look for the amount of ionizing radiation. In fact, you could do it in your basement if you were looking for radon. You could just take one of these things, put it in the basement, and eventually you would notice that the charge dissipates away, partly because of the ionizing radiation that's going through it. So he said, well, it's interesting that there is this ionizing radiation. Where's it coming from? And so there are there are more possibilities. The two thoughts that he had is, one, it's coming from the ground, something is radioactive in the ground, or it's coming from the sky. So his idea was to take it to the bottom of the Eiffel Tower, and the tallest building at the time in the early 1900s was the Eiffel Tower. It's about 300 meters or about 1,000 feet tall, and go to the top of it and see what's the difference. If he went higher, the air would tend to absorb that ionizing radiation, and so as he went higher, he should see that the ionization rate should go down. And in fact, that's actually what he saw. As he was at the bottom of the Eiffel Tower, the ionizing radiation was higher, and the rate that the gold leaves went together was much quicker. When he went to the top, they dissipated much more slowly. And that was actually one of the first evidences that there actually are, that there's actually radiation from the Earth. But the interesting thing about it was that when he went higher up, the rate of ionization didn't go down as quickly as he thought. It went down to about a half. And if he had gone to the top, I don't remember the exact number, but it should have gone down to like a quarter or something like that. So that was saying, well, that was a little puzzling, because it said that not only was there something radiating from the ground, but there also might be something radiating from the Earth. The next experiments, actually, Victor Hess took the same type of electroscope in a balloon. And as he got higher and higher up, in fact, he found that the rate of ionizing radiation went up, not down. And that's because the Earth's atmosphere protects us from a lot of that ionizing radiation. Okay, so the next thing I'm going to show is what you've probably seen a lot of times before. When we look at particle interactions, often what we see is these funny little tracks appearing. And I have a little movie that's going to play, and this is called a cloud chamber. Cloud chamber is basically a device that's filled with a highly ionized, superheated liquid. And when particles go through that liquid, they actually ionize the gas, and it causes little tracks to appear. So you'll see like one here. We'll wait a couple seconds. These bright white tracks. There's one on the right there. Those are actually cosmic rays that are just going through. They're hitting us right now, and they're going through this detector and leaving tracks behind. So if you take a picture of that, you'll often see something that looks like this. Now, as a physicist, we want to use these tracks to do something with it. We don't just want to take pretty pictures. They are kind of pretty. And what we do is we notice that you'll see that there are two particles that seem to come from the same place. We call that a vertex. And I have overlaid that. On top of that, there's a vertex going out with two particles coming out. But before it gets there, I'll just come back, notice that there's nothing that leads up to it. So what that means is that there's in this case, a neutral particle which doesn't interact with my detector, and all I detect is the two particles that come from its decay. So a neutral particle came in, it decayed, and left behind two other particles. The cool thing about that is that particle is called a lambda. When the lambda comes in and decays, it leaves behind two extra particles, a proton and a pion, and that's what we observe. If you remember from Keith Dennis's lecture, in physics, there's some really cool and important things, and those are conservation laws. In this case, we can take advantage of conservation of energy and conservation of momentum. And because of that, these two particles together have the net momentum and energy of the original particle. So if we can look at the tracks of what's left behind, we can actually figure out what caused that. So we don't actually have to see the initial particle, we can just look at what's left behind. Those are what we often call the daughter or decay particles. And so if we can measure the tracks of those two remaining particles, we can actually tell what happened before that and know that even though it's an unseen particle, that we have a new particle which may be the Higgs, for instance. So what can we do with those two particles? Well, with those two particles, as they go through our detector, they leave behind these tracks. You saw them in the cloud chamber. In this case, the tracks, if they're put inside a magnetic field, curve. We can measure that curvature very easily, and from that curvature, you can determine its momentum. Later, as you look at the particles as they swirl around and lose energy, they also, the number of dots in that picture changes. or the density of dots along the track. And if we can measure that density, we can then figure out what the energy of that particle is. And with those two things, the energy of the particle and the momentum, we can add them together and determine what the energy and momentum of the original particle was. And that's very important. We'll come back to that in a second, but I just want to leave you with that one point, that if you can determine the energy and momentum of the daughter particles, you know the energy and momentum of the parent particle, and that's the thing we're trying to find. Okay, so the types of technology that people have used are these imaging technologies. And these are kind of the things that you can tell just from the fact they're black and white, that these are kind of older technologies. On the left is Carl Anderson. He was one of the inventors of the cloud chamber that we saw those pictures of. On the right is another gentleman, I forget his name, but what he has is just basically a piece of film. And that film, if you just leave it out on top of a mountaintop, eventually you'll sometimes see particles that actually go through and decay. And there's an example of a particle that hit and actually splattered and created a whole set of new particles. So those were imaging technologies. Those imaging technologies are great because you can see all the tracks. You get precise information of where the track is. You can measure it to infinite precision. The problem is that you have to measure it to infinite precision because these poor women here, and they were mostly women, were called human scanners. They are actually given a number of pictures, and they had to measure every single dot along that to look through something like that on the left-hand side and determine what happened. As you can see on that by the late 60s, the amount of data they produced was so much that 3 days of data took these human scanners 2 years to go through that data set. Well, that's a problem. Well, not for me, but for these people anyway. So the next exercise was, well, how can we replace this imaging technology with another technology which can measure where the particles are, but doesn't require us to, as a human, go through and look for every single hit or whatever that is. And what I'm showing you here is an example from Ernest Rutherford's lab, where he was the person who discovered the existence of the nucleus of the atom. And you can see here his words. He said, what he did was he took alpha particles. Alpha particles are really just helium atoms without the electrons. They fired them at a piece of gold foil, and miraculously, some of those alpha particles actually bounced backwards. And in general, most of them went forward because they missed the nucleus. But every so often, they would hit the nucleus, bounce backwards, and you see particles ending up in the back. And as you can see, his quote was that it was as if you had fired a naval ship shell, a 15-inch shell, at a piece of tissue paper, and it came bouncing back at you. I mean, that's how extraordinary it was. Well, it's so extraordinary that he decided he didn't want to do the experiment. He actually assigned it as an undergraduate research project to a student at Manchester, and that was his project. And the reason it was so tedious is that to do this experiment, they actually had to look at a fluorescent screen and stare at it with a microscope in a completely dark room. So it took them 30 minutes to acclimate their eyes, and after they had been looking at this screen for a minute, they had to change out. So you can imagine both the human bias that can be introduced and also the pain on your eyes. I don't know how good their eyes were at the end of it. But the point is that this was an apparatus, they discovered this. They discovered that he was actually, along with, so Ernest Rutherford is on the right, and on the left is Hans Geiger, a name you'll come to see. And they realized this was a very interesting measurement, but this is probably not the way to measure it. So Hans Geiger actually came up with something that's now called the Geiger tube. This is a device in which there's a wire going down the middle of the tube, and the tube itself is filled with gas. When a particle goes through, it ionizes the gas and releases electrons. And those electrons can travel to the anode, the wire in the center, and creates a little bit of pulse. So you can actually measure this using a machine now as opposed to looking at human eyes. And you've probably heard this if you've ever seen old movies where they have a Geiger counter, you turn it on, and the thing starts clicking away. So that's kind of the next evolution in technology. Nowadays, we can take all those technologies and put them together. So now, when we come to the 21st century, you can put a bunch of Geiger tubes on top of each other. These, as you can see here, they're actually called proportional tubes. They're operated slightly differently. But you can stack them together, and when a particle goes through, you can actually see the particle hitting specific tubes, and from that you can measure where the particle went. You can actually measure the pathway. On the left-hand side, the top left, is a silicon chip, which actually has very, very fine gold wires etched on it. And those etchings allow us to actually do the same thing. We measure when a particle goes through that silicon chip, we can actually measure where the particle went through to within a few microns. It's amazing. You can, and a micron, if you know, is a millionth of a of a meter. And then finally, instead of actually having to try to look at the density of bubbles along that pathway, we can use a device like the one on the left. It's called a calorimeter. Just like the word calorie, it just measures energy. So we can take this device here, and by watching a particle enter and create a shower of new particles, we can actually measure the energy. So with these three technologies, we can now enter the digital age, and we now have a device which we can hook up to a computer and read the information out. We don't have to depend on those human scanners, and that's what we do now. So we're now entering the age of the LHC. This is a picture of the LHC tunnel. So Keith Dean has talked about it. This is currently the world's largest synchrotron that's ever been built. And what you're seeing is you're looking down the tunnel of it. In fact, it looks like it's straight. It's so big that you can barely see that the tunnel curves a little bit to your right. Inside the tunnel are these big blue objects, which are magnets. And those are the magnets that are slightly steering the particles as they try to go around this very large tunnel. And this is actually a picture with actually a image superimposed on top of it. So they make a little bit of a cutaway. And the two tubes that you see in the center are actually two tubes which are filled with protons. So in the LHC, we have protons going one way, which are going to collide with protons going the opposite direction. And when they collide in the center of a detector, they can actually produce some of these new particles we're looking at. This device was very interesting. Most accelerators up until this time actually used a particle and its antiparticle. If a particle and antiparticle are in the same magnetic field, they'll bend in opposite directions. But if the particle and antiparticle are in the same tube going in opposite directions, they'll bend the same way. So most accelerators up at that time use particles and antiparticles and put them in the same tube. Here, what we use is both protons. Protons both have the same charge, so you'll see there are two tubes. So these magnets actually have a very unique configuration such that you can bend protons going this way and protons going that way. And the way it does is the magnetic field on the farthest tube, say, is pointed upwards, and the magnetic field on the inner tube is pointed downward. So by these very unique magnets, we actually are able to produce the LHC. But before we go there, I just want to kind of give you a little bit of history of where we went. Dr. Ruiz mentioned the fact that in the late 80s and the early 90s, there was this grandiose idea to build this thing called the Superconducting Super Collider, the SSC. And the work on this, actually construction began in 1991. About that time, the University of Arizona created something called a decision package, which actually built up the particle physics group. And actually the reason that I'm here today is because the University of Arizona, the state of Arizona, invested in the idea of having a particle physics group here that could take advantage of this device. Unfortunately, unlike Sam Gralla said with regard to the LIGO experiment, this experiment started out it was costed, I think, at $2 billion. The cost rose to $4 billion, and by the time they canceled in 1993, it had ballooned to $12 billion. So that's a number that I guess got a little bit hard to swallow at the time. So what did we do? Well, we decided, well, what else is around? So we decided we would go to Europe. And so we have joined this experiment called the Large Hadron Collider, or the LHC. And this is an amazing device. It's 27 kilometers in circumference. It's actually on the border of France and Switzerland. It actually crosses the border. The yellow line is the border. It actually crosses it 4 times. There are no interdictions. It just keeps going unimpeded. And anyway, I'll stop there. And it traverses the whole countryside. Our experiment, there are actually 4 experiments. There's CMS, ATLAS, LHCb, and ALICE. The 2 ones that were involved with the discovery of the Higgs particle were CMS and ATLAS, but since we're on ATLAS, we'll just focus on that one. But I did want to kind of point out some of the really interesting things. When this tunnel was built, it was the largest civil construction project before the tunnel was built. So that's a fairly amazing thing. It was so big that when they were digging access tunnels to get down to where the tunnel had to be, they had to actually freeze the ground around it so they wouldn't disturb the groundwater. And then they sunk concrete around that. Once the concrete hardened, they let the ground thaw, and they didn't have to worry about the groundwater. But when they were sinking the tunnels, they actually had to do that. And in addition, the tunnel is so big that it's actually tilted up towards the Jura Mountains, which are towards that way. That way. And the reason that it's done that, so it's about 1.4 degrees tilt, the reason it's done that is because it turns out that the rock that they wanted to drill through was more conducive to drilling at that point. And what it actually did was it raised the LHC from being a few hundred meters underground to just about 100 meters underground all the way through. The other thing that's really cool to me is that when it rains, the tunnel actually gets bigger. And that's amazing because when they actually had a different apparatus in there, and that apparatus had to account for the rainfall because, excuse me, they could actually see the energy of the particles colliding change when it rained, and also when it was a full moon. So it was, both the tidal effects and the rain had an impact just on the size. I mean, that's pretty amazing. So I said you have to have the accelerator. The accelerator that we use is the LHC. The detector we use is the Atlas detector, and I was told I can't walk outside this white line, so I'm going to do it. But this is a person inside the detector. This detector is 6 stories tall, and it's the size of half a football field. So it's actually quite amazingly large. And it's the rate of data that it has to deal with is about 1 billion collisions per second. Just to give you some other numbers, there are 100 million signals that come out of this device. That's maybe not so large, but when you think of where they have to come to into one place, that's a lot. And the amount of data that we actually write to tape, so this is actually going to tape. This is not the amount of data produced by the detector. The detector produces more data, and then we look at the data as it's coming off the detector and decide whether or not to keep it or not. And so we only take, I think it was 1 out of 100,000 or 1 out of 10,000, 1 out of a very large number of the events actually are written to tape. Most of them actually end up on the computer floor. And this is what those pictures have become. Remember, we had these cloud chamber pictures of ghostly particles that would kind of appear in the detector. This picture is a transverse view of the detector. So if you think of the Atlas detector as a big can, the 2 protons collide down the axis of that can. At the very center of it, so in the center of this picture is where the protons collide, and then they produce other particles. One of them could be the Higgs. This is actually an example of a Higgs decaying into 2 electrons and 2 muons. The 2 muons are indicated by the red, and the electrons are those green towers that you kind of see there. You can see it maybe a little bit better here. What's interesting about this picture is that there's a lot more going on than just the Higgs, right? The Higgs is happening way over here on the left-hand side, and all the stuff that's happening in the middle, all those other squares, I don't know if you can see them, the colored squares, are actually other interactions from protons that are also happening inside the detector. So one of the things that we have to do is look at not only the Higgs decay, but all the other stuff that's produced at the same time and figure out which of them are Higgs particles and which ones aren't. And that's what we have to do as an experimental group. And so you can see this environment that our experiment is embedded in is actually a very challenging environment to work in. I do want to say one more thing about the Atlas detector. So in 1993, they canceled the SSC. Throughout the US physics community, it was actually quite a shocking time. People were kind of worried, what are we going to do? But my colleagues were smart enough. This is John Rutherford and Mike Shoup. They were actually at CERN at the time testing their detector, which was going to go into the SSC. And they walked across the cafeteria, found the spokespeople for the Atlas detector and said, hey, we've got a detector. Maybe we can put it into your machine, into your device, or our device into your detector. And the original design of the Atlas detector has these 2 big red globs, which you can see circled on this diagram. And what Mike Shoup and John Rutherford did was they said, if you take our device, we can put those devices well inside the detector. And if you do that, you'll find that, and they did tons of simulations, you'll find that the detector actually performs much better, that the amount of extra junk that's produced by having those detectors outside the detector will be going way down. They actually showed that with a lot of simulations, and it's true. It actually did reduce the background, and that design was accepted by the Atlas management and was the only US group to actually have a significant impact on the design of the detector itself. And so in some sense, I owe my career to my colleagues who were able to demonstrate that that their choice of detector and design would have a significant impact on the Atlas detector, and they did that. Okay, and this is that group there. It's a relatively small group of people, and this is the detector that they actually end up building. We built it in the basement of the physics building, which is just a block or so over from here, and they shipped it to Europe, and it's been installed and working great. Okay, so when we look at before we turned on the LHC, this is what they did an informal poll at Fermilab and asked all the scientists there, what do you think we're going to see? Well, you can see there's no consensus. There's kind of a wide variety of things. Obviously, the Higgs kind of rolls to the top, but it wasn't everybody's preferred direction. And if you're a mathematician, you might try to add these up. You'll realize it adds up to a number bigger than 100%. People are allowed to vote twice. And even then, you can see they didn't, there was no consensus about what they would see. And my favorite, supersymmetry, was way down there on the list. So what I'm going to show you now is that, remember that that when you take the daughter particles of this particle like the Higgs and decays, you can measure its momentum and its energy. Well, with those two quantities, it turns out, and I'll show you how in a few seconds, you can actually reconstruct the mass of the particle that produced those daughter particles. And so what I'm going to show you here is a plot of the mass of every particle in the ATLAS detector that decayed to 2 photons. And we started taking data in 2010. The data taking took about 2 years before we could say anything definitive. And so what you're going to look for, see again, is that you're going to look to see whether or not, as we're taking data, you can see any sort of anomaly or bump in the distribution of reconstructed masses for this Higgs. And this is what, oops, that did not work. Okay, so this is what happened. You can see at the very top, you'll see the dates. 2011, not too much going on there. There's a red line to guide your eye. 2012, we're taking more and more data, and all of a sudden you start to see something appearing. And right about July 12th, the experiment decided that we had enough data to claim that we actually saw something. And what you can see here, there's a blue line showing what you would have seen if there was no Higgs particle. And on top of that, you can see the data, which is the black dots. And you'll see that there's a little bit of a hump. And that is the evidence for the Higgs. And on July 12th, there was a party. We always have a party. The man all the way on the left is Francois Englert, one of the originators of this BEH theory. On the person next to him is Peter Higgs. Unfortunately, Bru had died already, so he didn't get to live this. Remember that these guys came up with the theory in 1960. This is now 2012, so over 50 years ago after their original thing. The person on the very right is the Director General of CERN. I can't remember who the guy is in the middle. And this was amazing. Well, it was amazing for 2 reasons. One, Higgs and Englert had never met each other. This is the very first time they met each other when they discovered the Higgs. That's kind of cool. But the other thing that it did was it allows us to actually say, yes, after 60 years, we've had this theory, which everybody thinks is the theory of how the standard model works. And now we actually have proof that it exists. It took us over 50 years to figure out that this was right. So even though the theorists had this idea, and they were, it wasn't widely accepted, but people started to really believe it was true, it still took us 50 years because we had to have the right technology, we had to have the right group of physicists, and we had to have the right environment, someone that would actually fund a machine that would cost billions of dollars and yet would produce this. So I did want to say one thing about these bump hunting experiments. That's what we call them, really. So remember that you have daughter particles that come out. We can measure their energies and their momentum. Well, with this very simple equation, it's not that hard. You can take the energies, add them up, square them, take the momentum, add those up, square them, and subtract the 2, and the square root of that, right, you can put it into your calculator. You don't need a spreadsheet. You can actually just do it in a calculator. Gives you the mass of the particle that produced those 2 particles. And there produces a bump. So if you see that bump, just by doing a little bit of algebra, you can actually prove to yourself that you've actually produced this Higgs particle. This is the paper that actually resulted from that. This is the ATLAS paper. You'll notice a couple things. It says observation. That's a very important word. It means we actually saw something. If you saw just a search, it means you didn't see anything. So observation in the search for this Higgs boson, it's a long title, but basically said we found it. The paper ran to 29 pages, and 10 of them were every single author who contributed to the experiment. There are actually almost 3,000 authors and about almost 180 institutions. However, the University of Arizona was 7th in the list of institutions, and we had 11 authors on that paper. So where are we with this? Well, in this chart of everything that we said, maybe nothing, something unexpected, supersymmetry, my favorite, extra dimensions, so far we're left with the Higgs boson, nothing else so far. And to some people, that's actually a problem. The supersymmetry really was one of the high theories that people thought would explain kind of the next bit of everything, including possibly dark matter. But we're kind of left with a bit of a conundrum. So where do we go from here? Before I do that, I just wanted to mention that in physics, you might not be able to, actually you can't read any of these, but these are 9 of the papers that I've had over my career. And I just wanted to point them out because, as I said, there are some key words when you read papers. When you read the title, the first thing you'll look for is search. Search means you didn't see anything. And all the blue ones were searches. We didn't see a thing. The white ones were papers where we actually measured something. And that's very typical in particle physics. Actually, most of the time, we measure nothing. I would say probably no more than 20% of the papers that I have my name on, and it's a lot, did we actually see anything. All the rest of the time, we have that word search. Now, you might say, okay, well, he's just a failure. He was only batting 200. But actually, that's not true. The thing is that when one, hyperactive thumb. When one measures nothing, you actually are telling people something. One thing you've done is you've told people, oh, we've already explored this area of physics space, and we don't see anything. That's important because the next people come along do want to know that you already looked there. If you looked there and you didn't see anything, they shouldn't have to look there. And the other thing is that you inform the physicists, the theorists, that their theory is wrong. That's actually important too. I mean, not because we can just kind of rub in their face, but because it's important that they know that that particular theory they came up with was not the one that actually is the way the world works. And so even though you might say I'm not batting particularly well, we do always publish even those results where we don't see anything. And in fact, as you can see later on, the majority of papers since I've been at the LHC have been nothing, 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 no supersymmetry. So where do we go from here? Well, the data that we've taken, you can see we measure them in these funny units. The amount of data we measure in this unit called an inverse femtobarn, or FB-1. All you have to know is that as that number gets bigger, we have more data. So the green line shows the data that we took when we first turned on the experiment in 2011. We actually took quite a bit of data for the time. In 2012, that number grew to 22 of those units. And in 2016, which we've just finished, we've even gotten more data than that. Well, our plans are to, by 2023, which is not that far away, to have almost 100 times more data than we have now. And currently, my group and the other faculty members at the U of A are working on upgrading the detector so we can take even more data up to another factor of 10 or 100 times more data than we currently have on tape. So that's what we're trying to do. And in order to do that, we've been working on these chambers. In fact, we've been building, oops, where did it go? There it is. We've been building these electronics boards to mount on these chambers because we have to increase the readout rate of the detector in order to keep up with the amount of data that we're taking. There are 15,000 boards that we're going to mount on the detector. So we have to build and test 15,000 boards and then go mount them on the detector. And that's why we have graduate students. No. Actually, that's not true. That's why we have undergraduate students. And so actually, that's not really a joke. We do take our undergraduates out to CERN, so it's actually one of the perks. And while they do have to replace the boards, they also get an experience of working on this detector, which is kind of a once-in-a-lifetime experience. So where are we going? What I've done now is I've described this thing called the standard model. The standard model describes everything in that yellow little pie shape, 5% of everything we know about the universe. The rest of it we know nothing about. So what I've been doing with my group is we've been actually looking in this purple chart because nobody knows what to do about, well, that's not quite true, but the lighter blue 69% dark energy, that's a whole different ball of wax. But we can do things on dark matter at the LHC, and so that's what we're doing. I'm working with a bunch of theorists who have come up with a theory of a new kind of dark matter called dynamical dark matter, which could be produced at the LHC. And so one thing I hope you'll find through this talk is that the reason that I think physicists have been able to advance the field the way they have is because there's a really unique collaboration between the theorists and the experimentalists. You know, the theorists sometimes have the right answer, the experimentalists sometimes fool them and come up with something different, but that collaboration between the experimentalists and theorists is what really provides that impetus for finding new discoveries. And so here at the University of Arizona, we have a group of theorists, we have a group of experimentalists, and of course we have the apparatus. Thank you very much.